Hello everyone, this is Virash and I will be presenting our paper Learning to Count Everything, which is a joint work with Udbhav, Thu and my advisor Min Hoy. So the goal of our paper is to build a visual counter capable of counting objects from any visual category. Towards this end, we propose few-shot adaptation and matching network, abbreviated as FAMNAT, which requires only a few examples to generalize to any visual category. Let's see if the previous visual counting approaches can also be used for counting objects from a large number of visual categories. So these counting approaches use a CNN to map an input image into a density map, and all the pixels in this density map is summed to obtain the final count. Now these approaches can handle a single visual category at a time and require expensive annotation for each new category. Hence, it's difficult to scale them to handle a large number of visual categories. In this paper, we propose a new counting task called few-shot counting, which when solved would allow us to generalize to any new visual category based on only a few labeled examples. Let's make the task more concrete. So the input is an image along with a set of bounding boxes denoting the object of interest to be counted, and the output is the overall number of objects of interest present in the input image. Here's our architecture for tackling the few-shot counting task. So the feature extraction module extracts convolutional features from the input image. The ROI pooling layer extracts the features for the exemplars from the locations of the bounding boxes. The feature correlation layer correlates these two features, which results in a set of correlation maps, which are used by the density prediction module to predict the final density map. Since the location of few exemplars is known in the test image, we propose to utilize this information to adapt our network to any new visual category at test time. So we propose two different losses for the adaptation. The first loss is called min count loss, which is based on the idea that since each bounding box contains at least one object, the sum within the density map at these bounding box locations must be at least 1. So this constraint can be enforced by the min count loss here. The second loss that we use for adaptation is perturbation loss, which forces the density values within these bounding boxes to stay close to a Gaussian, and this constraint can be enforced by the perturbation loss. Here ZB is the density map within a bounding box, and G is a Gaussian kernel. Now, since there does not exist any dataset which can be used for training few-shot visual counters, we collected a dataset called FSC147 for the task. So the dataset consists of over 6,000 images, and it contains images from over 147 classes, and each image comes with two types of annotation, which is bounding boxes for the exemplars and dot annotations for all the objects. Shown are few images from the dataset, and here we show few more images. Here we show few input images with the exemplars, the ground truth maps, and the corresponding prediction obtained by FAMNAT. For more quantitative and qualitative results, please check out our paper. Our code and data is already available on GitHub, and if you have any queries, don't hesitate to ask us at our poster. See you all at CVPR. Thank you.